Okay, so hi everybody, thank you for coming. Welcome to our monthly Canvas talks, which highlight the fantastic research that's being carried out by postdoctoral fellows in Canada. Postdocs in Canadian astronomy produce a huge fraction of our published papers while they're precariously employed in temporary positions. So this talk series is to recognize that impressive work. I'm Samantha Lawler. I'm a professor at the University of Regina. I'm hosting this meeting from Treaty 4 land, the territory of the Nahiawak, Anishinaabeg, Nakota, Dakota, Lakota, and the Métis-Michif Nation, where it was just announced today that a horrifying number of unmarked graves were discovered at one of the most recently closed residential schools. These territorial acknowledgements prior to public events are a first and important step toward reconciliation for those of us who are settlers and settler immigrants like myself. Today's speaker, Alexa Villaume, is a postdoctoral fellow at the Waterloo Center for Astrophysics. The University of Waterloo is situated on the Haldimand tract, land that was granted to the Haudenosaunee of the Six Nations of the Grand River and is within the territory of the neutral Anishinaabe and Haudenosaunee peoples. Prior to Waterloo, Alexa completed her PhD thesis at the University of California, Santa Cruz. She's an expert on astrostatistics and applies these techniques to many different physical scales in the universe. So thank you very much, Alexa. Take it away.
Well, thank you, Samantha, and thank you for the invite, and thank you for everybody for coming today and giving me a chance to tell you about what I've been working on. So, as you can see from my title, I'm going to be talking about probing the extremes of galaxy evolution with new stellar population synthesis models. And here on my title slide, though, I'm giving you a little foreshadowing to what I'll be talking about more specifically, which this isn't a galaxy. This isn't an image of a galaxy. It is an image of a Milky Way globular cluster. And the reason I have this on my title slide, just to give you a little preview, is one of the things that I hope to convince you of today is that globular clusters are really the frontier of our understanding and refining our understanding of galaxy evolution. But before I get into all of that, I know that this is a diverse audience, so I'll just give a little motivation of why we study galaxies and why our theory of galaxy evolution is so important. The short answer is that galaxies are basically at the nexus of every astrophysically important phenomenon. So the way we currently think about galaxies is, of course, we have this great, huge cosmic web. Within that cosmic web, dark matter halos form, and galaxies form within those dark matter halos. Galaxies then, in turn, provide the environment for star formation, planet formation, etc. And so this is all kind of packaged into what's called the concordance lambda CDM model of galaxy evolution. And so this is what goes into cosmological simulations, this semi-analytical models. This is how we understand a lot of these phenomena and processes. But what makes galaxy evolution so difficult to understand is the fact that the scales involved, the physical scales, the time scales, the length scales are span many orders of magnitude, which is difficult for us to, impossible for us to model a priori completely. And furthermore, an additional complication is that the direction of the effects here don't just go from large scale to small scale. We also, and the point of galaxy evolution theory is, basically connecting our distant past to our present such that we can make predictions about dark matter, galaxies themselves, and star formation. It's all supposed to come together like that. But as I was saying, another thing that makes this so difficult to understand and to model and come up with a cogent theory of is that the direction of the effect does not just go from large scales to small scales. The effect also goes from small scales up to larger scales. So galaxies provide the environment of star formation, and then things like stellar feedback, AGN feedback, the effects of stellar evolution go and in turn affect galaxies as we see them today and affect those evolution of galaxies. We also use observations of galaxies as tracers of dark matter. Right now, we're on the cusp of many new observational facilities, like the Rubin Observatory. And one of the main goals of these observatories is to use galaxies to trace and test different cosmological theories and parameters. And so we need to know how things like star formation, how things like AGN feedback and so on, the processes that happen within galaxies in turn affect how we see galaxies and view them, and then try to use them to understand cosmology as well. So this is a very challenging problem, but it's part of what makes it such an interesting and rich field, in my opinion. And so I said that I alluded that there's our theory of galaxy evolution is incomplete, right? And there's a lot of various studies doing very detailed analysis and comparing observations to the predictions of semi-analytical models or cosmological simulations, and that's great, important work. But I also just want to point out that part of the proof of our limitations of galaxy evolution theory is that we keep getting surprised by new types of objects. We make a better instrument, we make a better telescope, and suddenly we see something that we never expected before. And so I'm just giving a little example of this, which is, we really had this idea of dwarf galaxies and what was the dwarf galaxy population. And then there was this discovery of ultra diffuse galaxies, which I'm showing here, and this is all to scale. So the idea behind these ultra diffuse galaxies is they're very large, but then they have very low stellar metallicity. And so that was a complete surprise. That did not come out of our predictions from cosmological simulations. And this is a little preview. I'll touch base on this again near the end of my talk. And so this is also why I wanted to emphasize why it's important to look at the extremes of galaxy evolution, which is definitely something these ultra diffuse galaxies represent. But we've now known about, it's not all bad news. We've known about galaxies as a concept now for nearly 100 years, the famous Great Debate. And we've learned, quite a lot about galaxies. So one of the key things that we know about galaxies is this color and morphological bimodality in the galaxy population, which is basically here on the left. I'm showing the late type spiral galaxies. They're forming stars. This is what our Milky Way galaxy is. And then on the left, I'm showing early type galaxies that are seem to be very simple, smooth. They have old stellar populations. They're not forming new stars. And so one of the big things we've learned in the last 100 years of studying galaxies is that those designations, late type and early type, are completely backwards. Hubble got it wrong, and that's okay. But we now know that the late type galaxies are the beginning of galaxy evolution, or the younger stars, or have the younger stellar populations, while the early type galaxies have the older, deader stellar populations. And so one of the big questions in galaxy evolution is how do galaxies make this transition from blue ringed star forming to red, dead, old? And this is a major question because the quiescent galaxy population is growing. It's been growing over cosmic time, and it basically represents every process of star formation. These galaxies were once star forming. What was their star formation like? What stopped their star formation? And then how did they grow after these massive elliptical galaxies grow after they stopped forming their stars? And so we have a pretty simple view of the structure of elliptical galaxies, which is we kind of break them up into two parts, which is their inner core of a few kiloparsecs. And these, in our current understanding of how these galaxies form, these were already in place, already formed, and already quiescent red nuggets at Z of about 2. And then the extended envelope forms through accretion up to what we see as these galaxies in the present day universe. And so the simple structure we have for these galaxies corresponds to our simple view of their evolution, which, like I said, is just this: we have this in situ core component here on the left, that is from an early dissipational phase, and then extended growth from dry mergers. And so this is often called the two-phase formation of galaxies. But we're in a bit of a bind, because when we go and try to look at the details of these galaxies, there are a lot of properties of these galaxies that we still just cannot explain. And so I've taken to calling this the quiescent galaxy crisis, to indicate how important it is that we understand these properties of these galaxies. And so the first one is when we look at the stellar populations of these inner regions of these galaxies, that red nugget core that I just showed you on the previous slide, they have these very extreme abundance patterns that we cannot self-consistently explain with our current understanding of star formation processes. And so the figure I'm showing here on the right shows the velocity dispersion of a set of galaxies. So higher velocity dispersion is an indicator of a more massive galaxy. And on the y-axis is magnesium over Fe, which is an alpha abundance, which is used as a star formation rate indicator. And so these galaxies are supposedly forming their stars very quickly. The most massive of these galaxies are forming their stars very quickly, very early, and then nothing. And it just, I can't get into all the details, but we can't really explain it all. And it gets worse once we also take into account not just the abundance measurements we're measuring for these galaxies, but also the idea that these galaxies have a variable IMF. So this is, now I'm showing you two examples of a galaxy where we've got the Milky Way IMF over a certain important feature, and then we can see in one of these galaxies a so-called bottom-heavy IMF fits these galaxy spectra more accurately than a Milky Way IMF. And so this indicates that these galaxies formed a much larger population of low-mass stars than we would expect, which is, again, very difficult to reconcile with the abundance measurements.
Excuse me, could you tell me what the axes were there?
Oh, I'm sorry. I dropped the labels at some point here. Yeah, so the axes here are, this is a wavelength feature. This is over the wing forward band, which is one of the important IMF sensitive features. It just means it's a surface gravity sensitive feature rather than a metallicity or abundance feature. And then, yeah, so this is just a zoom in on the spectrum, where in the black and shaded region as the observation with the uncertainty, and then the colored lines are showing the best fit models for the various IMF parameterizations. Is that, are we good?
Well, yeah, I'm wondering, the y-axis is ratio.
It's just arbitrary. It's just arbitrary flux. It's just a little zoom in section of a spectrum over a specific spectral feature.
Okay, thanks.
Yeah, no problem. And another issue with our understanding of quiescent galaxies is that we can't match the outskirts of massive elliptical galaxies with the properties of present-day satellite galaxies. So here I'm showing a figure from Jenny Green's paper from 2013. This is the massive survey, where she is comparing the abundance patterns of her galaxy sample, which are these massive early type galaxies, and this is a radial spatially resolved data, and the thing to take away from this figure is that the outskirts of these galaxies do not match the centers of the satellite galaxy population that we would expect to make up the outer halo of these galaxies. And then this has also been indicated in other ways through very deep imaging, see Lombardi et al., also globular cluster counts. I'm going to touch on more on this later, but it's an issue when we say we think these galaxies grew through dry mergers, but then we can't find the population of galaxies that supposedly make up these outer halos. So my key questions in my research are, what were the characteristics of the progenitor population of the halos of massive elliptical galaxies? And then also, how did stars form in the biased environment of the early universe? And is there a diversity of quenching mechanisms? And then how does quenching occur and under what conditions? And so these are kind of what I'm going to show you how I address and deal with these questions throughout my research. And so, but I'm going to try to cover a lot of ground in this talk. And what I really want, if there's one thing I want you all to take away from this talk, is that galaxy evolution is an interdisciplinary field. And so it is I think it's going to be key in refining our understanding of galaxy evolution to try to keep all these aspects in mind. And I think having different aspects of galaxy evolution, looking at different extremes of galaxy evolution, are how we are going to make progress in coming up with a consistent theory of galaxy evolution. And so just to give you a little, my perspective of galaxy evolution is I view it through a lens of stellar astrophysics. Basically, the buzzword of this is galactic archaeology, which is basically just using the properties of long-lived stars to reconstruct star formation history and assembly history of galaxies. And so here, I'm just showing an example of this, of how we use galactic archaeology in the local group to understand the Milky Way. So this is showing stellar metallicity versus alpha abundance on the y-axis. And we've got Milky Way stars in black, and then the stars from various dwarf satellites around the Milky Way in the various colors. And what this is, how this works in practice is basically we use stellar abundances as chemical clocks. And this works because the stars that produce alpha abundances, like magnesium, are different and shorter lived than stars that produce iron metallicity. So at the beginning of, in the early phases of star formation, the massive stars have been born, and then they have died and exploded as type 2 supernova, which enriches the environment with alpha abundances. And so you, at the early stages or through a short process, you have an alpha enriched environment. And then if, with long enough time, when type 1a supernovas start to go off and enrich the medium with iron metallicity, then that starts to increase the stellar metallicity and dilute the alpha abundance. And so, and there are different other factors that can control the shape of this kind of diagram, which is the IMF will increase the magnesium abundance, and then how quickly the enrichment happens, how quickly the star formation happens, really determines the location of this breakpoint, which is called the knee. So if star formation happened very quickly and then stopped, you freeze the abundances of that stellar population as magnesium or alpha enhanced. And then more extended star formation history, you have higher stellar metallicity and less enhanced magnesium because it's been diluted. Now, this is what is possible in the Milky Way. And now with some heroic efforts by various people also starting to get out to M31, but basically this is what is possible with resolved stars. And we do not have spectroscopic access to resolved stars at all outside of the local group to get abundances like this. And so far what people have made do with is spatially resolved integrated light measurements. And so here again, I'm showing you the same figure from Jenny Green's massive survey. And so this is, this really was made possible with the advent of IFUs. And here, so I'm showing you here on the left, the measurements from the IFU data. And then here on the right, I'm showing an example of a massive elliptical galaxy that was part of her survey. And so stellar population gradients allow us to get at these sub-kiloparsec scales where this very important star formation processes take place. But IFU data can only get us out so far. So here now I'm showing the extent of the typical extent we can get from an IFU of the stellar light of a galaxy like this. And this is, this makes things, there's a great progress, but there's still a lot of complications for this. One, the inner halo region is going to be this complex mix of in and exit shoot populations. And we just cannot disentangle those populations from integrated light, even spatially resolved integrated light. And then also, you can see on this figure, there's a wonderful, beautiful, deep image of a massive early type galaxy, and you can see the extended envelope around this, that the IFU data just is not sensitive enough to capture spectroscopically. And so, getting out to the outer halo region would be really one of the cleanest tests of assembly theory for these galaxies. So to get into my own research, I want to do a little activity, if nobody minds. So I want you all to think of the earliest paper by publication date that you can think of that describes galaxy formation through hierarchical structure growth or two-phase assembly. And type it into the chat box, but wait, I want to give everybody 20-ish seconds to think about this. And when I say go, I want everybody to enter their paper that they can think of into the chat box. So I'll give everybody a little time to think. And this is not a quiz, this is just me being curious about what people think. And then I just have to figure out how to get the chat up while I'm screen sharing. Oh, okay, go ahead and answer. Zoom, I gotta get the chat up. Okay. All right, only Joel Rodiger answered. Nobody else? What year was that? Oh, 1962. Really? I thought by then people were still on the monolithic collapse theory. Wow, that's very interesting. No worries, Samantha, it's okay. This activity works better with other audience sometimes. Yeah, so basically what I was doing this as a lead in to introducing the concept of using globular clusters to study galaxy evolution and the assembly of galaxies. And so back in, this goes back to Cyril and Zin paper on the Milky Way globular cluster population, which looked at the radial gradients of the globular cluster population, which I'm showing here in this figure. And what they noticed is that these outer halo globular clusters, which I've indicated in red, have this flat metallicity gradient. And their conclusion was, in attempting to account for these properties, we have been led in each case away from the notion of an isolated, uniform, homogeneous, collapsing protogalaxy, which was the dominant paradigm of galaxy formation at the time. The observations appear to indicate a more chaotic origin for the galaxy. So basically what they did is they came up with this idea that purely through empirical observations of the Milky Way globular clusters, that the Milky Way galaxy formed hierarchically. And so I just want to point out that this paper came out in 1978, which is pre George Blumenthal's paper, pre-lambda CDM. And so people often talk about like, well, under the lambda CDM paradigm, we think galaxies formed hierarchically. Well, actually, we had that idea before lambda CDM just from observations. Part of what made lambda CDM such a strong contender is that it matched these observations. And so this was for the Milky Way galaxy. This was in the 70s. And where are we at today? So because of this, galaxy GC, this connection between GC systems and their use of being able to understand the assembly history of galaxies, huge investments have been made into large photometric surveys of GC systems. And so here now I'm showing you that same image of the massive Rowley type galaxy, and overplotted in red now I'm showing the next generation Virgo cluster survey GC catalog around this. So you can notice that there's many thousands of GCs around this galaxy that extend very far out in galactocentric radius. So this makes GCs very useful in trying to understand galaxy formation. And one of the main, results of these photometric studies of globular cluster systems is this idea of bimodality as a universality in GC systems, which basically means if you measure the colors of all these GCs in this galaxy and other galaxies, and you plot up the color distribution function, make a histogram, you will see this bimodality in these color distributions of these GC systems. And this has kind of, for the last 20 years, the paradigm has been the blue GCs are supposed to trace the accreted population, and the red GCs are supposed to trace the in situ formation. So they formed along with that nugget, that red nugget at high redshift. And then the blue GCs came in with the satellite galaxies that built up those stellar halos around those massive galaxies. And so this has been great. But there's still quite a few limitations, and we've seen, the importance of A, spatial information, and B, detailed abundance patterns in trying to fully recreate the assembly histories and the formation histories of the stellar populations of these galaxies. Furthermore, GC formation still a major unsolved problem, and I won't have time to really get into that today, but you can, if you're interested in this, you can look at my paper from 2019 for details on how this can affect our interpretations of GC colors and potentially bias our constraints on galaxy evolution that we try to use for these from GC systems.
We're at 30 minutes.
Yeah, thank you. So what I've been working on is using, trying to apply the tools of galactic archaeology and spectroscopy to GC systems to recreate and understand the formation histories of galaxies. I may have mentioned before that, for the galaxy light, the field population of the stars, we went from basically having a single value integrated light centered on the galaxy to, with the advent of IFUs, to being able to get spatially resolved information of the stellar populations here. And because stellar population models have historically been designed for elliptical galaxies, when these instruments were made and popularized, made common, getting that kind of, getting what I'm showing here, which is a radial gradient of stellar metallicity for M87 for the integrated starlight, didn't require updates to the stellar population models, really. But GCs are globular clusters are a very different population than what is typically been in mind when people have been developing stellar population synthesis models. So the key thing is that they can be much lower metallicity than these centers, or even out to an RE of these galaxies. And so inference of detailed stellar population information of globular clusters had been held back by limitations in the SPS models. And this is what I worked on at the beginning of my PhD thesis, is developing a new stellar library to create a new set of full spectrum precision stellar population synthesis models, with the idea of using these and applying these to more exotic systems than were possible before, including globular clusters. And so this is just a little GIF of my stellar library going up an isochrone. And so what this meant was that I could now apply full spectrum SPS models to fit globular clusters, individual spectra of globular clusters in a galaxy as distant as M87, which is 16 megaparsecs away. And so here I'm just showing some examples of fits to red GCs, an example, here in M87, blue GCs are going to be typically less metal rich, and so their spectral features are going to be weaker. And so here now, I'm showing you again where the M87 integrated starlight is, and what we get when we can fit the M87 globular clusters, which I fit a few hundred of these globular clusters with these stellar population synthesis models. And so you can see how amazing it is, how far out we can probe using globular clusters as these discrete tracers and these fossil records of the formation history. So now the question is, well, how do we can't just, now we have to figure out how to separate all of this into sensible subpopulations, because we don't think, right, we have this bimodality paradigm. We have blue globular clusters that are supposed to be metal poor and trace the ex situ population, and metal rich globular clusters that are supposed to trace the in situ population. So getting those metallicity gradients separately for those stellar populations is very important and be a really key constraint for galaxy evolution and formation models. And this has been done by a lot of people. And so here now I'm showing you a figure from this paper by Forbes and Remus from a few years ago, which it was a meta-analysis of getting these color/metallicity gradients of different GC systems separately for the blue and red populations. And so there's a big problem here in this figure. And I'll give you a hint of what this big problem is that these points, the same color indicates the same system measured from a different study. So the problem is that there's no consistency in the slope measurements among different studies of the same system. And so if we wanted to take these gradients and really compare them to things like mosaics or even FIRE, which are starting to either include globular clusters or starting to try to form globular clusters in those simulations, we wouldn't be expecting to get a very sensible answer out of this, because these gradients are inaccurate. We don't have a way to measure them accurately. And this is for a few reasons. So there's a lot of, you might think fitting a gradient is as simple as just fitting a line to data, which if only. So one major issue is that we are working with projected distances, which adds systematic uncertainty to the stellar population gradients. So here in this GIF, I'm showing on the left true three-dimensional distance of a mock globular cluster system. And on the right, I'm showing the projected distance, the gradient of versus the projected distance for various slopes from very flat to pretty steep. And what you can see is that there is going to be uncertainty added because we don't have access to the true 3D distances, but we can't account for that a priori because we don't know the slope ahead of time. Furthermore, there's going to be covariance between the subpopulation assignments and the subpopulation parameters. So now again, I'm showing you mock data of different metallicity distributions of different underlying metallicity gradients with two subpopulation systems. And if we apply the methods that people have used before for that, what was included in that Forbes and Remus figure, we can see that there is just not a lot of accuracy because of this covariance. And so all of these things, the projected distances, the covariance between the subpopulation parameters that we're trying to measure with the subpopulation assignments, all go into not having accurate gradient measurements of the different subpopulations in globular cluster systems. So what I did is developed a hierarchical Bayesian mixture model to mitigate these issues. And I know some people are getting wary of Bayesian stuff as a buzzword, but really it's not. And I don't have time to go into all the details now, but I hope, if you're interested, I encourage you to look at the paper. And I just want to say, like, stats is very important in actually enabling the physics, and it's something that we have to be thinking about, particularly in this case. So just I'm going to skip this and just refer you all to my 2020 paper, or you can ask me questions afterwards about how this model works. But basically, what you get in the end is, after a statistical deprojection of the distance and a simultaneous fit for stellar population parameters with the assignments to the individual globular clusters and subpopulations, we get much more accurate metallicity gradients for these subpopulations in these systems. And I'm going to focus in on this, what I'm going to call the inner halo region right now, which is everything within 40 kiloparsecs. And I want to get your attention to this remarkably flat gradients in the inner halo of the globular cluster populations here. So why would these gradients be flat? So it can make sense for the metal-rich globular clusters. If a major merger, which can happen, brings in a population of metal-rich globular clusters, it can disrupt and mix it with the in situ metal-rich globular clusters and lead to a flat gradient. But what about the metal-poor globular clusters? Why would it's very strange that their subpopulation gradient is flat, because minor mergers that we would think would bring in the metal-poor population should lead to a negative metallicity gradient. That's just dynamical friction. One explanation, and I go into this in my paper, is the possibility that the metallicity gradient of the ex situ metal-poor globular clusters is being diluted by an in situ population. And so this is a simulation from Mir Mendelker's globular cluster formation model, where he used the Villaume simulations to come up with a way to form globular clusters in metal-poor globular clusters in massive halos. So this is an in situ metal-poor globular cluster population that leads to this very high redshift formation of the blue globular clusters that stay with these massive galaxies. And because of the way the intergalactic medium works at this high redshift, this would lead to flat metallicity gradients. So if we could identify these in situ metal-poor globular clusters, this would be a very exciting window to the high redshift intergalactic medium and the very early star formation epoch of massive galaxies. And so I just want to remind you again about what I said about these very strange, extreme abundance patterns and the IMF variability in these galaxies. And identifying these metal poor globular clusters that formed with that population could really be an amazing window, an amazing fossil record into this very early star formation history. So, and I just want to just make a little plug, look out for forthcoming work from a graduate student that I've been working with since I've gotten here, Chloe Chang. She's doing really great work on really detailed fits to high signal to noise globular cluster data that we're going to get IMFs and abundance patterns, and it's going to be great. So this just emphasizes the importance of being able to identify and separate and disentangle the in situ and ex situ populations in these galaxies. And there's just still limitations in the current data and models that are holding us back from what I am calling big G, galactic, what we can do in the Milky Way archaeology beyond the local group. But it's clearly very important to pursue this avenue. And so in 2020, when I first developed this model, to get abundances and alpha abundances, the data was not, did not have high enough signal to noise where I could measure these abundances at an individual globular cluster level. So I stacked it, and there were some interesting results. But what I'm working on now in my postdoc here is developing the statistical framework to move beyond bimodality, and then also have higher spatial resolution of the abundances. And since I didn't get a chance to explain my model, I'll just flash this up here. And if anybody, if you're interested, please come talk to me. But this is what I'm working on currently, is developing this tool set to be able to separate more precisely the subpopulations of globular cluster systems, and then also get abundance patterns out of those subpopulations. And so basically, one thing that needs to happen is not just development of the statistical framework, but also the population synthesis models need to be further developed to better work with globular clusters and understand the formation of globular clusters themselves. And yeah, the hierarchical model needs to be extended. So going back to my key questions. So I really think that spectroscopic measurements of individual GCs provide a unique means to disentangle the in and ex situ stellar populations of galaxies beyond the local group. And this is going to be really key in advancing our understanding of galaxy evolution. And so future work, developing the SPS models, developing the statistical framework, but then also more efficient data collection. So I'm really excited about the Mauna Kea Spectroscopic Explorer. I cited a couple times work from the Next Generation Virgo Cluster Survey, which I really think is one of the great legacies of Canadian astrophysics. And so I'm really excited that this new instrument, which seems perfect to study spectroscopically globular cluster systems, is going to be online eventually. Okay, so wrapping up. There's one last question I had in my key questions that I haven't talked about yet, which is the diversity of quenching mechanisms. And I'm going to come at this a little bit sideways first by talking about the progenitor population, again, of massive early type galaxies. Just bear with me, it'll make sense, I promise. So now, we were focusing on the inner halo before, but now let's talk about the outer halo. And I'm not going to talk about the metallicity gradients of the outer halo. These are the first spectroscopically derived stellar metallicity measurements of the outer halo of a brightest cluster galaxy, M87. And the important thing is that these stellar metallicities that we measure for these globular clusters, they indicate progenitor population of dwarfs galaxies, about 10 to the 8 stellar masses, using the mass metallicity relation. Cosmological simulations predict more massive progenitor satellites than that. They predict about Milky Way mass satellites as the progenitors of these massive early type galaxy halos. So the stellar populations are off between what we'd expect of Milky Way population and what we're seeing in the outer halos. The GC population counts are also discrepant here too. M87 and other galaxies like it, their halos just cannot be explained by shredding a bunch of M31 and Milky Way galaxies. So is there something wrong with the simulations? Or is the progenitor population different from the surviving population? And you might want to remember what I was saying about part of the quiescent galaxy crisis earlier with Jenny Green's work is the stellar populations of these outer halo galaxies don't match with the current satellite population. So now we're going back to UDGs. So again, these were discovered very recently, astrophysically speaking. These are a seemingly novel set of objects with sizes like giant galaxies, sizes like Milky Way galaxies, and luminosities like dwarf galaxies. More interestingly than that even is a lot of these ultra diffuse galaxies have a lot of UDGs, or I'm sorry, a lot of globular clusters around them. So we have there's been some under theory when these were first discovered that maybe UDGs had overmassive halos. They were failed galaxies in some way. And this could, this could be a population that made up the halos of these massive early type galaxies because they're rich in globular clusters, they're metal poor, and they may have high dark matter compared to their stellar mass, which would kind of solve the discrepancy between predictions from cosmological simulations and the observations we're getting. However, you might have heard this is highly controversial and a lot of people get really angry when you suggest it. So this is kind of the fundamental tension is, do ultra diffuse galaxies, are they a part of the canonical dwarf population, or do they somehow represent something special about galaxy evolution that we hitherto have not understood, and that they can help us resolve these issues we see elsewhere in these massive early type galaxies? And so here I'm just showing where ultra diffuse galaxies fit in on luminosity versus size. And what I'm going to be talking about now is this particular ultra diffuse galaxy, Dragonfly 44. It's one of the largest ultra diffuse galaxies found, and it's been found to have a populous globular cluster system, which is a bit controversial still. People are going back and forth in the literature about the exact counts of this globular cluster. Dragonfly 44 exists in the Coma cluster, just FYI. So I said Virgo was far away at 16.5 megaparsecs. Coma is about 100 megaparsecs away. So these are difficult things to study, and especially when, by definition, these objects are very low surface brightness. So, but the best way to know if this is just part of the normal dwarf population is through its stellar populations. So here I'm showing the mass metallicity relation for dwarfs, including local group dwarfs and coma dwarfs, and there's pretty much a continuous relation. And a lot of simulations use this formation, this figure as a constraint on their models. And so this is the normal dwarf population. This is what has been measured so far for the ultra diffuse galaxy population. So it's a really large scatter for the UDGs, but also look at the uncertainties on these measurements. They're really large. So is it just an effective, is the scatter just an effective imprecise measurements? So I was fortunate enough to work with a team that got KCWI data on the Keck telescope, which is amazing IFU designed for very low surface brightness cosmic web spectrograph. So it's designed for these kinds of observations. And so I got a very high signal to noise spectroscopic measurement for DF44. And what I find is that DF44 genuinely falls below the mass metallicity relation of the canonical dwarf population. So this could be a sign of an unusually catastrophic quenching mechanism. Moreover, I was also able to get spatially resolved spectroscopic measurements for different stellar population parameters for DF44. And I found a flat age gradient, a positive metallicity gradient, and a negative magnesium gradient, an alpha abundance gradient. And so we can look, and what I did is I compared how DF44 looks in how the gradients of age and metallicity for DF44 compare to both the observations of canonical dwarfs and to the models, the simulations that have been made to explain the local group dwarf toroidal population. And what's interesting here is that when you take into account all the factors, which is the gradients, the overall just mass weighted ages of these populations, and their kinematics, so whether they are rotation supported or pressure supported, DF44 is not consistent with observations or predictions from simulations of the canonical dwarf population. So it could really be a genuinely strange galaxy, and coupled with what looks to be like its very quick formation mechanism, it might actually be a true example of a failed galaxy, so to speak. Whether it's a failed galaxy that exists in an overmassive halo is a different question, but it does seem to have some exotic star formation and quenching mechanisms that affect how we see it today. And so now, to just bring it back all together, typically, and this is again something we know from the NGVS survey, dwarf galaxies have color offsets between their field star populations and their globular cluster populations, which indicate separate star formation events. But what we find with DF44 is that this inner region, the inner, kiloparsec or so region of DF44 matches with the metal poor globular clusters in abundant space, in metallicity versus alpha space. And so the theory I and my co-authors put forth in this paper is that a formation of a massive starburst event formed the GC system and then caused DF44 to self-quench. And so that's where we've landed. And so there seems to be accumulating evidence to support the plausibility of UDGs as the progenitor population of massive elliptical galaxy halos, which is really cool. It means that these galaxies would have existed in much greater abundance at earlier times, which is an interesting testable prediction. And this quenching mechanism is quite unusual. We usually do not think of galaxies with the stellar mass of DF44 as being self-quenched. We always think of them as being environmentally quenched. But my measurements really indicate an unusually early, unusually quick, and unusually catastrophic quenching mechanism, which really makes it very interesting to study further and explore more star population gradients of UDGs to see how common these particular gradient signatures are. So I'm also getting star populations of the globular clusters would also be very interesting. And then we could do direct abundance matching between the globular cluster populations around massive early type galaxies and the globular cluster populations around UDGs. And that would be a really smoking gun kind of thing of these UDGs formed the massive halos of early type galaxies. And that is, again, going to be tough. Again, DF44 is 100 megaparsecs away. It takes a lot of observing time to get data for that. But I'm really excited about the prospect of JWST. So I'll put up my key questions and then a restatement of my summary here. And I'll just again flash that galaxy evolution is an interdisciplinary field. I hope I brought that through to you all, and I can take questions now. Thank you.
Thank you. That was a great talk. Let's see, we've got time for a couple of questions. William, you ask fantastic questions. I'm going to see if anybody else wants to ask first. Does anybody else have a question? No? Okay, go for it, William. Thank you.
Thanks for the plug, Samantha. Much appreciated. In your graphs, in your plots, what worries me, what I wonder about, let's say, is that there seems to be a lot of scatter, and there doesn't seem to be a lot of range. Usually less than like about 1 dex. And you say,
excuse me, can you specify which figures you're talking about?
well, a number of them, but you could talk about, for example, the one that says no consistency in slope measurements, for example. There was a label on there, for example.
Oh, yeah. So that's a figure I took from another paper to motivate why
Sure.
I felt, yeah.
Sure. I'm talking about the field in general. I'm not targeting your work necessarily.
Mhm.
What I'm saying is there seems to be a lot of scatter, and the range seems to be usually less than 1 dex in many of the plots that I've seen, and with non-negligible error bars. So how can you trust the gradients that you get? And I mean, there are systematic effects. Some of them you can characterize. There are the known unknowns, as they say, and there are the unknown unknowns. So if you just have a few points in certain places, they could change things drastically. So how do you have confidence in the results is basically my question.
Yeah, so I mean, first I would refer you for the M87 gradients. I really do, if you're interested in this, I do recommend you read the paper, because that was the main point, why it was necessary to develop this hierarchical model to measure these gradients. Because exactly like you say, there's the measurement on the individual uncertainties are large. Yes. And then, but more importantly, there are these systematic uncertainties, which when we're talking about globular cluster systems, it's the projected distances, and it is the fact that these are aggregate populations. And so discerning and disentangling the subpopulations is really the key thing that we have to do. That's the key systematic uncertainty in these measurements. You know, we can deal with, you know, large uncertainties on individual measurements. Those are taken into account when we measure gradients. But the systematic uncertainties of how to decompose subpopulations from an aggregate system, that's the key thing that I addressed in my hierarchical model. And so, yeah, if you want to talk to me more about it, I'd be happy to. And then, but I also recommend, explaining Bayesian statistics in a Q&A is a tall order. So yeah. And then, so were you also concerned about the gradients on DF44? Was that also an aspect of your concern?
Well, I mean, I remember you talking about the inner part of a galaxy, and it has a flat gradient, but I saw lots of scatter, so it didn't look necessarily flat to me, right?
So what I showed here, I'll go back. Oh, I have no idea what just happened. Sorry, I think Keynote just
died on you.
Died on me. But yeah, so weird. Okay. I don't know what's happening with my Keynote. Sorry about that. I'll just say that with the gradients, what I measure, I get full posteriors on the slopes and on the intercepts of those gradients. I don't assume anything about the gradients before I measure them. And so what I showed you are the full posteriors of the gradients for the metal rich and metal poor subpopulation in the inner halo of M87. And what I quote as the best fit gradient and 1 sigma error bar are the 16th, 50th, and 84th percentiles of that posterior. So those definitely take into account the measurement uncertainty, and they definitely, so within 1 sigma uncertainty, those gradients are flat.
Right,
basically.
But I mean, with Bayesian statistics, you put in your prior, but you can include known unknowns in there somehow, but unknown unknowns, I mean, yeah.
I mean, you can include unknown unknowns because that is what you do when you marginalize over parameters. That is what you do when you can include, which I did, an additional uncertainty factor. So to account for the unmeasured uncertainty on my metallicity measurements. But again, the constraints of the talk format prevented me from going into detail there. But if you want to take a look and talk to me more about it, totally happy to, because I do think it's the way to go.
Right, thanks.
Okay, and with that, we're at the hour. So thanks very much for coming, and we will see you in a month. I forgot to look up who's next, but we have another fantastic postdoc lined up for next month. Thanks, everybody.
Thank you, Samantha. Thank you, everybody.
Thanks very much, Alex. Thanks, everyone.
Recording.